Thank you for your generous invitation and kind introduction. My role today will be to sacrifice myself as the bad boy on the block by trying to replace combustion engines at large by electrical machines. This presentation is going to demonstrate how the usage of copper in renewable energy systems may be reduced dramatically by as much as 80%. There are also ways to replace the scarce copper conduction material by aluminum entirely. My presentation will be structured in 3 parts. First, reducing the usage of fossil resources to 0 by 2060, and what the associated copper primary demand will be by making combustion engines obsolete. Second, ways to replace the copper conduction material by aluminum altogether. And third, making existing electrical actuators ways more efficient and cheaper, and how that can be achieved by a new paradigm. This slide shows fossil resource usage with respect to 100% in 2020. Characteristics from top to bottom, worst case, global basis scenario according to the International Energy Association. And the best case down here is global supreme, which aims at reducing fossil resources to 0 by 2050. This slide shows primary copper usage with respect to 100% in 2020, characteristics from left to right. The global supreme, global EE, and global ME scenarios show a sharp increase combined with a massive start of the expansion of renewable energies. This is followed by a stepwise approximation of a 500% peak demand in 2030, which already subscribes all major copper mines in this world. The extremely high 800% peaks in global aid are caused by the delayed and then compensatorily high expansion of countries at different speeds globally. So there are reasons to be very careful with copper demand, I think. Copper electrical conductivity exceeds that of aluminum by 50%. Thermal conductivities are practically the same. Therefore, an electrical motor with aluminum windings needs conducting bars with 50% more cross-sectional area, given the same efficiency. At the same time, aluminum stator and rotor windings have 45% less weight. In essence, the dynamic performance characteristics of aluminum motors may easily outperform those of copper motors. This is the case for this 360 kilowatt traction motor generator on slide number 5 here. Electromagnetic sensors and actuators usually use cylindrical coil arrangements to generate or measure electromagnetic induction. Cylindrical coil arrangements can be converted into flat grid structures by cutting them along a surface line and then connecting the cut ends of each side with a bus bar, which is what you can see here. The bus bars eventually are best terminated by current sources. In this way, equivalent grid structures are obtained, which are basically flat and free of intersections. Path or angle information is encoded with variable conductor density, as you see in the lower half. The same is true for the angular distribution of current densities in the stator or rotor of an electrical machine. The arrangement in this slide therefore shows a perfect flat displacement sensor. The sensor signal is typically evaluated when the signal terminal voltage is 0 by short-circuiting the ends of the sensor itself. Please let me share 2 transient simulation products that were developed for my students originally. In the left half, we see an angular sensor recording the rotor speed for the engine control. In the right half, we see a 3D motor model with stator rotor induction in the XY cutting plane. The excitation frequency is 50 Hertz. 2 phase currents are applied to the first and third quadrant and to the second and fourth quadrant respectively, shifted by 90 degrees against each other. The red induction vectors emanating from the stator rotate clockwise and continue to generate a uniform induction field inside the rotor, which also rotates clockwise. So this is what we can actually animate. And you will see the stator just staying in place and the rotor rotating clockwise under the internal induction field. Let me come to the real meat, which is a ladder steps engine, any pole, any phase induction motor, which can have, as the name implies, any number of poles and any number of phases. In this LSE engine, the rotor on the right side is simply copied over to the stator, and it looks basically the same as the rotor. That's the new thing. The only difference is that the top end ring in red color allows for the sourcing of the individual transient stator phase currents. The stator depicted, for instance, features 5 adjacent stator slots per phases ABC with a constant pitch of 15. Sourcing of currents may be done by either incorporating active currents or by allowing individual planes for the phases A, B, C. It's important to note that the end ring short circuits all starter windings and thus closes all stator slots across the end ring individually. We can look at this by seeing an animation of the transient startup of a 2-pole pair 3-phase induction motor with a constant stator field frequency of 50 Hertz, while the stator currents are being ramped up to 500 amperes per slot. So what you can see, hopefully, is that the stator field rotates anti-clockwise, whereas the rotor rotates clockwise. Same startup procedure here, with the focus shifted to the magnetic flux density vector rather. The simulation shows the 4 magnetic stator poles rotating counterclockwise in pairs, with the rotor rotating in the opposite direction, just what we have seen with the magnitude of the magnetic induction. One and the same stator may be used to build any of the existing electromagnetic motors, like the induction engine, what we have seen here, or a synchronous permanent magnet motor, or a reluctance motor. For comparison, the performance of this ladder steps engine motor I just showed you is the same as the one with the aluminum windings, namely 300 kilowatts, 360 kilowatts at 30,000 RPM. Let me summarize. Ladder steps engines do only exist at Peer Technology at the moment. They are completely new. Kolyakuzi and I think that the United States, European Union, and China are in a race for electric mobility, and only one competitor can win. That's presumably the one with the best patents. The ladder steps engine patent that I just showed you blocks any further development because it's a basic patent, not just a device, by a new paradigm, and it's patented in the European Union, the United States, and China, and of course also in Canada. So what we would like to offer actually to invest more into this new paradigm, and we would like to help with a global head start in electric mobility, and it also applies to many other electrical systems. Thank you for your attention.